Right. So I'm just going to like go through the problems. What's link? Okay, so the first question is grass plant. So the abridged statement is you have a tree and you want to support two types of queries. The first one will be to add one to the edge, to every edge along the path. And the second query is just to create the edge value. So well, if this is if this tree just a line, it's quite simple. We can just use like a fabric tree. And because trees are just many lines with HLD, we can just use HLD and convert this tree to like the lines. Yeah. And we can just use family or segment tree to support our range add endpoint query. Our second question is milk visits. So the abridged statement is we have a tree, then the nodes have types. So we have to answer queries on whether the path from A to B contains a type C. So you will think about this, right? Like, let's say, what if the tree is a line? How will you answer this question? If the tree is a line, well, what we can do is we can kind of like, because the queries are offline, so we can split them up based on their types, right? And once we split them up based on their type, we can just answer all the queries of the same type together. So how we do that is for every node, we give the node a value of 1 if it's type that we are processing. Otherwise, it's 0. Then whether the path from A to B contains a type, it's just whether the range sum of that is larger than 0. So you can just use the fragment tree, fabric tree. Yeah. Then because we kind of like want to clear our previous type that we process, and we can't just like mem set it to 0 because that will be too slow. So you can like kind of like it's just like you just update with -1 to our previous type. And to convert this line solution to a tree solution, you can just use HLD again. Yes. So basically, heavy light decomposition is converting a tree problem to a line problem, and you still have to solve the line problem. Okay, are there any questions so far? Yeah, okay. And also like, even if you know the solution, right, you should try to like code it out because half of competitive programming is like programming. So it's not just problem solving. Yeah. And when you code your solution out, you might like face a lot of errors and bugs. And knowing how to debug your code is very, very important. Okay. The next one. So factories. So the abridged statement is if you have a tree, you have to answer online queries on what's the shortest distance between to sets. So this is actually very similar to our problem of linear and tree. Linear and tree is basically like you have a set of like all previous updates, and our query just create our current only one node and the set of every other node. While factories will want it's like it's basically the same thing. You just have to look through every node in set A and update it. Then you query the middle distance between every node in set B and all updates so far. So factories is basically just a linear and tree extension. So we just look through all the nodes in A, then look through all the nodes in B. And because it's like multiple queries, right? After we do this, right, we have to like reset our values to 0 or whatever the default value is. So to do this, right, we can basically just like store like we can just like look through all the nodes that we have visited, then we just reset the values for those. Okay, race. So the abridged statement is if we have a given tree with some weighted edges, right? Then we have to find a path with total weight k, and uses the fewest number of edges. And if there's no such path, we have to output -1. There are a lot of methods to do this question, and we are only going to go through the Centroid decom method because this lecture is on Centroid decomposition and individuality. But other than Centroid decom, we can also use like set merging if you know what that is. So let's first consider a node U. And if the path passes through U, we can just DFS of U and find one or two paths which start at U. So it's like U to X, which add up to weight K. So the reason why I say one or two paths is because like U can be like one of the endpoint of the path. And in that case, there's just only one path which starts at U. Otherwise, right, we can remove U from the tree and we are left with multiple subtrees which we can solve again. But if you do this naively, it'll be O of n squared. Because the thing about it, we have the DFS on every single node. And that will be n squared. However, if we choose U to be a centroid, and we will recursively solve every subtree using that centroid as U first, then our time from C will just be reduced down to n log n. And this is basically like exploiting that we can DFS on every single centroid subtree in our centroid tree. So there are other solutions including set merging. So set merging is basically like we don't have to use a centroid, but it's also more complicated because you have to use like some other data structure to like combine the path or something. Yay. Okay. The last question, invasion. So the bridge statement is that in a tree, we have to find the maximum length of interval L to R such that there exists a connected subgraph that has at most k nodes, and all nodes with L to R are part of the connected subgraph. So if we have a line, the question is quite simple. We can just use like sliding window or 2 pointers to like store our kind of like our current range. But now it's a tree, so we can use, but we can also use 2 pointers on L and R too. But the main idea is we cannot just use like it's going to be very difficult to for us to count like how many nodes our how many like nodes that L all the nodes that L to R encompasses because we have to compare this with K. So instead of finding that, we can find like the total length that it uses. And the length is a bit easier because we can just add up distances. So how this works is that the length of our subtree is the distance from the first node by pre-order to the LCA of all nodes, plus the distance of every node to LCA of that node and the previous node. So let me just give you an example. So let's say we have one, two, three. Yeah, so let's say we need the nodes like let's say we need the nodes 5, 13, and 6. So the LCL of all nodes is 2, right? So we'll basically be adding up this distance, which is the distance from first node to the LCL of all nodes. And the second one means the LCL of 5 and 6 is 4. So we add this distance. And next one, LCL of 6 and 13 will be yeah, this distance. So that will just be like the length of our total subtree. Yeah. And this is yeah, it's a bit cancerous to code, but it should be doable. Yeah, so that is the like editorial for the problems that I'm going to go through. Are there like any specific other problems that anyone wants me to talk about? Hello, it's quite good. If not, if there's like any other question, then you all can just ask me.